For this lecture on Pascal's principle, I'll be using a video from the Khan Academy. Something about his work that you should know is that it's all done on a similar program that I use, but he draws out a lot of stuff, and it takes a long time there, and he goes at a kind of a slower pace. But some of the videos I do like a lot. And on this one here where he goes through on Pascal's principle, this is in chapter 11.5 in your textbook. And just so you know, as you get in here, because we're kind of jumping into the middle of his lecture, he has drawn a weird object where he's pushing a piston down on one side, and the object is filled with a fluid, water or oil, anything like that, an incompressible fluid. And he's pushing a piston down on one side, and he's going to kind of review it really quickly and then go into everything else about it. So, without further ado, Khan Academy.
Doing the last video before I run out of time, I said that, okay, conservation of energy tells us that the work I put into the system, or the energy that I put into the system, because they're really the same thing, is equal to the work that I get out of the system, or the energy that I got out of the system, right? And I said, well, that means that the input work is equal to the output work, or that the input force times the input distance is equal to the output force times the output distance. That's just the definition of work. And let me just rewrite this equation here. If I could just rewrite this exact equation, I could say, so the force, input force, and let me just divide it by, just for kicks, let me divide it by this area. Because what I'm talking, the input here, I'm pressing down this piston that's pressing down on this area of water. So it's input force, and let me say that, times the input area. Well, let me call this input. Let's call it the input 1. Let's call the output 2 for simplicity. So there's going to be some, let's say I have a piston on the top here. Let me do this in a good color, brown. Brown is a good color. So I have another piston here, right? And there's going to be some outward force, F2. And this is the general notion is that I'm pushing on this water. The water can't be compressed, so the water's going to push up on this end, right? So the input force times the input distance is going to be equal to the output force times the output distance, right? This is just law of conservation of energy and everything we do with work, etc. So I just I'm rewriting this equation. So if I take the input force and divide by the input area, switch back to green, and then let's say I multiply by the area then, and then I just multiply times D1. You see what I did here? I just multiplied and divide by A1, which you can do. You can multiply and divide by any number. Right? These two cancel out, is equal to the same thing on the other side. F2, I'm not good at managing my space on my whiteboard. F2 over A2 times A2 times D2. Hopefully that makes sense. So what's this quantity right here? This F1 divided by A1. Well, force divided by area, if you haven't been familiar with it already, and actually if you're just watching my videos, there's no reason for you to be, is defined as pressure. Pressure is force in a given area. So this is pressure. So we'll call this the pressure that I'm inputting into the system. Pressure 1 times, and what's area 1 times distance 1? So that's the area of the tube at this point, the cross-sectional area times its distance. Well, that's equal to this volume that I calculated in the previous video, right? We could say that's the input volume, or V1. Pressure times V1 is equal to the output pressure, right? Force 2 divided by area 2, right? That's the output pressure that the water is exerting on this piston. So that's the output pressure, P2. And what's area 2 times D2? So this area, the cross-sectional area, times the height at which, how much the water is being displaced upward, that is equal to volume 2, right? But what do we know about these two volumes? And I went over it probably redundantly in the previous video, is that those two volumes are equal, right? V1 is equal to V2. So we could just divide both sides by that equation, and you get the pressure input is equal to the pressure output. So P1 is equal to P2. So P1 is equal to P2 coming out. P2. And I did all of that just to show you that this isn't a new concept. This is just the conservation of energy. The only new thing I did is I divided, we have this notion of the cross-sectional area, and we have this notion of pressure. So where does that help us? Well, this actually tells us, and you can do this example in multiple situations, but I like to think of it if we didn't have gravity first, because gravity tends to confuse things, but we'll introduce gravity in a video or two, is that when you have any external a pressure onto a liquid, so onto an incompressible fluid, that pressure is distributed evenly throughout the fluid. And that's what we essentially just proved just using the law of conservation of energy and everything we know about work. And what I just said, that's called Pascal's principle, that if any external pressure is applied to a fluid, that pressure is distributed throughout the fluid equally. And another way to think about it, I mean, we proved it with this little drawing here.
Quick review from what we just saw. This is Pascal's principle, saying that the pressure on the wall at any one point enclosing a fluid is going to be the same no matter where you go. And as you change the area, therefore the force will change. And this is what we have when we have hydraulic lifts for cars, like in a mechanic's shop. So here we have our hydraulic lift. Once again, pressure is the same on both sides. This is because the work done by the input is equal to the work done by the output, conservation of energy. However, with the pressure being the same, the forces can be very different because the areas are very different. So, a small area will mean a much lesser force, whereas a large area means a much greater force. Here's a problem using the car lift example. The car lift has an output plunger with a radius of 9.0 centimeters and used to lift a total weight, that's the car and the plunger, of 21,600 newtons. What is the pressure used in operating the lift? And what is the force of the input plunger if it has a radius of 4 centimeters? Thank you very much and have a good night.